All right, so the light is on, and finally someone has remembered to charge the lapel so I don't have to stay stagnant on behind the desk. I just wanted to mention the announcement I put up yesterday. So there's two things coming up, actually one reoccurring, but also the National Science Quiz. So Sunday evening we've got some teams that are competing, so if you want to, just email Karen. She teaches 1220 if you intend to do that. But yeah, so we've got it in PG12 in the physics room, and you can have teams up to 6, and there's free pizza, so can't go wrong. Just email Karen. But also the physics seminar, which we're going to be holding every couple of weeks. So that kicks off today after a long-winded break due to COVID. And I'm first up because I was the only one that responded. So I'm presenting today, 1 to 2. Luckily, it's only 20 minutes instead of an hour, so it should be easier. But then also we've got a visitor from Colorado Uni, a PhD of Karen's, visiting for 2 weeks, Jonathan, so he's presenting as well. So if you've got some free time and want to learn about some of the research that I do as well as others, feel free to come along. The other thing I should mention again, because I will mention it until the class test happens, so there's no excuse for people not to know about it. Class test is occurring next week. It's on Friday. Opens at 8 a.m, closes at midnight. So you will be given about an hour based on when you start. There will be multiple choice questions and 2 long answer questions. So one question will be based on David's work, weeks 1 and 2, and the second question will be based on this week's work. Nothing on next week, just on vectors, SI units, dimensional analysis, projectile motion. So it should be fine. There's a mock test that you can try. That's more to practice the upload. So you will have to upload the document for 2 long answer questions. So that mock test can help you with that. So is there any questions before we move on about those? No? All right. If you do, you can always email David and he can help you out. So let's start this week, today's. So what we've covered already is we've covered some stuff on one-dimensional motion yesterday. So we just looked at the X direction and the Y direction, or the horizontal and vertical. So today we're going to look at how we can use the stuff we've learnt about vectors, as well as the stuff we've learnt about the motion in one dimension, to apply to projectile motion. And what we're going to see is that when we have something projected in a parabola or projectile motion path, you'll have both X and Y coordinates, and we can't really solve it easily without splitting those components up into the X and Y. So that's what we'll do. But first, we're just going to go back to our first lecture and look at vectors. So when we look at motion of projectiles, or in kinematics in general, we write the letter R. So what that R represents is the displacement vector. And so what you'll see is that we've got the I, J and K hat respectively, and they all represent the X, Y and Z. We don't do any Z this week. We only do 2-dimensional stuff, but it will come in handy later on. And it's good to remember. So we can have the change in position in the displacement using the vectors if we have R1 and R2. So we can rewrite that as delta R. So the vector arrow on the top, and then the change in that R, and we can use the final displacement vector minus the initial displacement vector. And we've represented that in this little graph. So we have our Y and X coordinates, and so R1 has some sort of Y and X direction, similar to R2, and so we can find the displacement, the difference, or the change in R, delta R, from points 1 to 2. And what we can do is just add up the X, Y and Z components respectively. So whatever values there are in that vector, we can add them up. Or the second method, and I'll show this in an example later, so you can either just plug it straight in from the vector notation, or we can separate them out into the X, the Y and the Z, add them up, and then rewrite the equation for the displacement vector. So this will equal the number here, and so on. And we can also integrate all these into the kinematic equations. So we have the velocity vector, so Vx, Vy and Vz. So today we'll see how we can have velocities in the X and Y direction, and then we can use those to split out the components into the x and y and solve using kinematics, or we could use the entire vector and implement that as well. And again, very similar for the acceleration, where we tend to have, for projectile motion, zero displacement, acceleration in the x direction most of the time, but we tend to have a constant acceleration of 9.8 or negative 9.8, depending on what axes you've drawn in the positive. So if you've drawn a positive y direction up, we'll have a negative 9.8 metres per second. All right, so we're getting a bit ahead of ourselves, but it's good. I like to repeat things a lot. So this is what it looks like collectively. So we have our velocity kinematics equation up the top here. So if we were just to write it as one individual vector equation, it would just be v with the arrow. But if we wanted to represent each component, we can do by simply putting the x there to represent the x component. And so you can already see that if this equation has an acceleration that is, for example, in the x direction 0, then the vx will equal the v naught, or the initial velocity in the x direction. So you can already see some simplifications that you can do for your problems. And however, we got vy equals the initial velocity in the y direction, and we can get the a, we replace that with g times t. So we can tend to use this equation if we know the initial velocity and obviously the acceleration due to gravity. We can use that equation to find t or v, depending on which comes first. Similar, we have the displacement ones, and we'll see how we can use the vectors that we're given, and we can separate those components out and plug them into the x and y, and then find this displacement vector at the end. So we'll find a value for x and y. And then the third equation, unsurprisingly, we can write it like so, and sometimes we can use it to find the change in displacement, x minus x naught. And most of the times you will be able to set the initial positions for x naught and xy as 0, depending on the application. So let's see how we can use this in application. We have this object, and again you'll be given all those equations on an equation sheet. And I also should say that given that this exam will likely be face-to-face, I know that we did it in semester 1 and David's applying for that again this semester, you're actually allowed a 1 A4 sheet of paper, handwritten, actually it doesn't have to be handwritten, it could be whatever you want, of all the notes that you want. So you've got the formula sheet that you can see at any time on campus, but also the 1 A4 sheet that you can take into the exam, because you're not expected to remember all this, especially with all the information you can get at hand. All right, so an object at origin t equals 0, so that's the time of 0 seconds. It has an initial velocity, so v naught there is equal to 1 I hat minus 3.2 j hat metres per second. So that means we have an initial velocity in the x direction of 1 and an initial velocity in the y direction of minus 3.2. Okay, and we've got an acceleration vector as well, 4 I hat plus 3 j hat metres per second. And what we're asked is the position, velocity and the speed. So I'm going to show two methods of solving this one. So we're going to go to the document reader. And I've got it started here. Zoom in a bit. All right, so we've got the example there where we've got the velocity, initial velocity. It's up now. Acceleration, and we're asked to find the displacement vector, the velocity vector at 2 seconds. So that's what I've got here, 2 seconds. So we can use the vector, one of the vectors that we're given previously, so that r equals r naught, the initial position, plus v naught, the initial velocity, multiplied by time, plus a half a for acceleration t squared. And I should remember to put all the vector arrows on there. So what we can do is we can simply plug in these into the equation. So we can have v, well this one's 0 anyway, so that's 0 because we've got an initial displacement of 0, or you can write it out as 0 I hat plus 0 j hat, same thing. And we can then plug in the vector here for initial velocity. So that's 1 I hat minus 3.2 j hat multiplied by t plus a half, and then we've got the acceleration vector there, 4.0 I hat plus 3 j hat, and I've run out of room, but there's also a t squared at the end. So then you can just add all the like components up, so all the I hats and the j hats, and so you should get something like 10 minus 4.4, is that right? And that should be an I, and that should give you your displacement vector. And we can compare that in the next method of solving this as well. So now we've got the R displacement vector, so we have the position. We can put that into our velocity equation to find the velocity as well. So that velocity equation was V equals the initial velocity plus AT. And of course we've got both of those, so we can put those in as well. So V naught being 1.0 I hat minus 3.2 j hat, and acceleration 4.0 I hat plus 3.0 j hat t. And again we can add those together and we get, oh yeah, that's good. Just checking, all right, yep, so 9 I hat plus 2.8 j hat, and that's in metres per second. All right, and what we can do now, because that's just given us a vector, we can actually find the magnitude of that. So if you remember, we can write magnitude with those two lines, and we can use the trigonometry method, so that's just the square root of the squares. So 9.0 squared, 2.80 squared, and we get 9.4. Make sure you can still see. All right, so that's one method where you can use vector notation directly into the kinematic equations. The other method you can do, and in fact, I'll just show that. What's the time? Probably got time to go through it. We've got another example as well, so I might just show that on the slide with the working out, and we'll go through it. Wait for it to come up. Definitely slower in this room. All right, so we got the vector component notation. So this one, I've written out those two vectors again, but we can have the x equation there. So x equals x naught, or the initial position in the x direction, plus the initial velocity in the x direction times t plus a half ax t squared. And so what you can do is you can split those out. So the initial position is 0, so we put a 0 there. The initial velocity in the x component is 1, so we can put 1, and then obviously you've got t of 2 seconds, plus a half a in the x direction, which is going to be 4 times 2 squared for the time. And so when you calculate that, you get x equals 10 metres. And similar, you can do the same thing for the y. You can extract the y components out of those vectors, plug them into the equation, and you'll get the same thing as what we've done on the previous method, where we get a displacement vector of 10 I hat minus 0.4 j hat metres. And then you can put that into the separate component velocity equations for x and y. So we got, again, v naught 1, which is from here. The acceleration in the x direction is 4, and then respectively you've got the y components, and you can find the velocity. And again, we can use trigonometry, square root of the squares, to find the magnitude of the velocity. So they're the two methods. You don't have to show both. Just stick with the one that resonates with you the best, the one that you think that you can solve quickly. Obviously, the previous one was a lot quicker, so I prefer that one. All right, so let's move on to projectile motion now that we know how to use the vectors. And let's get this on.
We can now
extend our earlier example of a falling object in one direction to a more general case of objects moving through air. This is a vector problem. We have both y and x components. However, gravity is still acting downwards and is constant. By aligning our y-axis with the vertical axis, we can break the situation into two independent components. So the x component of the motion always has a constant velocity but no acceleration. The y component has constant acceleration, 9.8 meters per second, but changing velocity. So now let's look at our horizontal equations in the x direction. So we can get our velocity in the x direction, and that's going to be equal to the initial velocity in the x direction plus the acceleration in the x direction times the time. And this is equation 1. But we can simplify it using the assumptions we've already said. So we've said the acceleration in the x direction is 0. So we can simplify it to be the velocity in the x direction is equal to the initial velocity in the x direction, because the plus at cancels out with the 0. We can then look at the displacement. So x being the displacement in the x direction, this is equal to the initial displacement in the x direction, or the initial position in the x direction, plus the initial velocity times t plus a half at squared. And again, we can simplify this because we know that the acceleration is 0. So this equation 2 can now become x equals v0 times t, where you only need the initial velocity and the time. So we have our horizontal component. Now let's look at our vertical component in the y direction. So the velocity in the y direction is going to be equal, similarly to the previous one, v0 plus at. So this is our equation 1. But with this one, we know the initial velocity is 0, but the acceleration is equal to minus g. So this can be further simplified to vy equals minus gt. So you only need to know the time, because we all know the gravitational constant. Well, at least I hope you do by now. Or we could look at the displacement in the y direction. So the position in y is equal to the y0 plus the initial velocity in the y direction times t plus a half at squared. We know, again, that the velocity in the y direction is 0 initially. So the y position can be found by using the equation 2 here, where y is equal to the initial position in the y direction plus v0 times t plus a half at squared. But again, we know the initial velocity in the y direction is 0. So this can be simplified, and it will give you y equals minus a half gt squared. So all you need again is the time, which makes it easier when you're looking at solving these problems. Alright, so it's not always the case where we have an initial velocity of 0. Sometimes there is a case where you'll need to split the components of the initial velocity as well, and we'll see that soon. Also, it's not always going to have a starting position of 0. You might be hitting a cricket ball a few centimetres, I don't know, 30 centimetres up, or you might be on a rooftop, or your ball might land on a rooftop. Actually, there's an example of that next week in the tutorial. So all those things have to be taken into consideration problem by problem. So we're going to move on to projectile motion. So that's where we're given initial velocity, and it follows a path shown in the blue trajectory path. Obviously we got resistance, but we don't consider that yet. So we simplify things in physics and make sure that we can get a pretty good estimate of what to expect. So we're going to neglect resistance of air and the curvature of rotation of the Earth, and we're going to get a nice little parabola path like so, where we've got the y-axis going up, so we tend to have positive y direction up and positive x direction across the page. But again, that's something that you can change as well. We'll see that next week when we look at force dynamics, or the dynamics where we have force applications. So you can actually change the direction that you say is positive. All right, so we have our path. We have an initial velocity with the green arrow of v0. We've got the acceleration in the x direction set as 0, and we have this constant acceleration vector in the y direction as minus g. And that's only minus because we've established that up is positive. So if we were to have a look at that example that we had yesterday, where we had the ball going down the page just one direction in the y, you'll see that the balls actually match in line with every photograph. So what I'm saying is that every photo has been taken and these two balls are at the same distance. These two balls you can see at the same distance, and again these ones. So they're all travelling the same amount of distance, despite the fact one is moving in the x and y direction. And that sort of just reinforces the fact that we don't have the acceleration in the x direction. And so that's important to remember. And we've got some questions in the multiple choice ones that you can have a look. They sort of play around with that concept. So if we were to have a look at the vectors, and I'll actually look, we've got some simulations that I've put through the lectures as well. So if we start off with the initial velocity, so we have v0y and v0x, but the combined initial velocity is that green arrow there. And you can see that I've got a little angle, alpha. So that's the angle from the horizontal. And so this is going to come into play soon when we need to separate that initial velocity out into the x and y using the angle, as well as the initial velocity that we've been given, v0 here. Okay, so once we get the kickoff or whatever projectile motion's going on, you'll notice that the v0x is equivalent in the magnitude of that vector. So as you move across, we get constant velocity, whereas the velocity in the y direction will be 0 at the highest point. So we have no velocity in the y direction there. The only velocity that we have is the horizontal velocity. But one thing is that this orange acceleration is always constant. And also, if we have two spots on either side of that parabola, we'll have the y velocity going up and most likely opposite velocity going in the opposite direction, but same magnitude. So it's just playing that role there. All right, so I've got this projectile motion, and I think I've got it set on the vector one. So I've got this on Canvas as well, actually. If we go to the lecture notes for this week, if you wanted to have a go at home, I've got one on vectors, about adding them and subtracting them, if that's something that might be helpful, as well as a projectile motion simulator. So if we go here, I've got my cannonball set. I wonder if it's going to... Yep, that's okay. So that's our projectile motion path. And you can actually see those vectors changing in real time. I've slowed it down, and you can play around with the initial speed. So if we slow that down, the initial speed that we set, we're going to get a really small one. It's probably a bit too small. There we go. So you'll see that that range decreases. And we'll have a look at what factors influence the range. Can you think of any at the moment, other than the one I just showed you? Yeah? Launch angle, yep. So that's a really good one. So if we go, I'm going to clear this and go a bit faster. I've set the launch angle to 45 degrees here. And we can actually find a derivation to determine what angle will give you the best range. So if I was to change that up, we should get a higher height reached, but we're going to get a lower range. So we'll come back to this in the lecture slides, but one thing I want you to start thinking about was what happens if we increase the height. Does it have the same sort of angle? So the angle, the best angle, which we'll see in a moment, is 45 degrees. To get, if you want to get the biggest range, it depends on what your application is. But if you were looking at getting the best range, that's the angle. And we'll see that next, or soon. But first we're going to look at how we can separate those vectors of the initial velocity. So we have our v0 velocity. You've probably been given that, could be 27 metres per second. We can separate that out, and we might be given an angle, maybe it's 45 degrees. So if you're given a 45 degree angle and a velocity of 27 metres per second, you can actually derive the velocity in the y direction. So it'll be 27 sine 45 and 27 cos 45. And that's just an example. So you can easily separate those out, and then you can continue on using your y and x components for the kinematic equations. And so that's one thing, and it's usually one of the first steps involved. In fact, I'm pretty sure it could be for their class test next week. Yeah, so we've got the equations set here. So we have the x and the y positions we can separate those components out and we can then substitute them directly into those kinematic equations. So like I just said, the x is v cos alpha. We can put that in here, v cos alpha. So now we have 27 cos 45 degrees multiplied by t. So you can actually get a value. It could be, I think it's like 4.9 or something. So we can get a value here for the initial velocity multiplied by t. And so all we need to find is x. And we can find t, or if we know t, we can find x. And similar for the y direction, we already know what g is, as long as it's on Earth. So we have t, and you might need to find t. So how would you do that if we know v sine alpha and g? Does anyone want to yell out how we would do that? If we know all these, if we might know y is 0, we know these values, and we know a half g, and we need to find t. Quadratic equation, yeah. So there we go. So basically that's all the fundamentals you need to know to calculate any or to solve any of the problems that you'll come across for kinematics. Here. All right, and we can do the same thing for velocity. So we can find the velocity x, that will be v naught cos alpha, because we said that the initial velocity equals the velocity throughout that projectile motion. And then again, we can find vy, and that will be dependent on the time, because like we said, that vector magnitude changes throughout the pathway of that projectile. All right. Now I said about range. This is how we can find the optimum range. Do you need to derive this? No, you don't have to remember the derivation, but you should be able to understand how we get there. So what we've done is we're trying to figure out, or what we're going to do is trying to figure out the maximum range for the projectile. So if we have our initial velocities and we've separated them out into the x and the y components, so we have vx naught and vy naught, we can find the x direction. So now I've just changed the alpha angle to theta, and I've just replaced that into the equation. So it's important to remember to be consistent throughout whatever symbols you use, because it will change. And so we can use that, and we can find the x direction, or x displacement. And so we know that x will be equal to r. So that's the range. Again, I've changed the symbol from x to r, and that's the furthest distance we can reach with that projectile. So we can substitute in our initial velocity in the y direction, v cos theta, like I've written here, t. And what this is, someone asked me this in one of the labs this week, what do these numbers represent? This is our way of tracking the useful equations that we might have. So this one's called equation 1, and then I've got another one, equation 2, and you'll see that on the other side of the page, I'm substituting equation 2 into 1. So we'll get there, but just so you know, when you see it in the laboratory manuals, it will often refer to those equations that we've numbered. All right, so let's look at the x direction. We know the x equation, initial position, which is 0, plus the initial velocity, which is v naught sine theta, a half gt squared. So now we can substitute that in, and we can actually rearrange to get our time. So now it's 2 times the initial velocity in the y direction divided by g. So now we can actually substitute t into this equation here, because that's one of our unknowns. And what you should get is r equals 2 initial velocity squared, cos theta sine theta, which gives us 2 sine theta, divided by g. So now we know that the maximum angle, which is here, value of the initial velocity squared divided by g, is when sine 2 theta equals 1. And so from that, we can say that theta is 45 degrees. And so that's what we showed on the little simulation that we had. And so that's the equation for the maximum range. And we can get the maximum range at 45 degrees. And you can actually see that with that simulator. So we can go back to that simulation. I'm not going to show everything because it's pretty obvious now. So we're going to go back down to y equals 0. And I'm going to show 45 degrees. And what you'll notice is that there's always going to be, so the highest angle, the 45 degrees will give us the longest range, and then every other angle below that will hit a position twice. We'll hit that position with 2 different angles, if that makes sense. So we can go up to, let's go up to 50, and then we'll go down 5. Maybe I should have done it a bit faster, but that's okay. All right, so that's a little bit shorter. And this one's a little bit shorter too, but it should hit, oh, look at that. There you go. So it's going about the same distance. But yeah, so I thought it was going to be a little bit shorter. So the other thing we can add to this is air resistance. And actually I've already selected it, so that could be why it's a bit off. So we have air resistance, and if I go home, we can actually see different objects. And this is going to come up soon with drag next week. So you can pick a pumpkin. That would have large drag, wouldn't it? All right, so we can shoot a pumpkin. Let's shoot it a bit faster. Oh, now it's too fast. Okay. Yeah. And then we can add no air resistance. And we should see what sort of path we get. So obviously it's what you expect. It shortens the range a bit. So in reality, we do get some sort of difference in the range. And we see that in the next slides. So we're not going to look at how we can define that just yet. But I think it's the second lecture, maybe Wednesday next week, we will. So obviously we do get this air resistance. So the pathway that we've been looking at is without, but the pathway with will have some sort of force acting on the projectile, reducing the range that you would expect. So I guess my next question was regarding the height. So imagine you have I'm standing here, 45 degrees gives me the longest range. What about if I go up 100 metres? Would that still be the same case? So would 45 degrees still give the maximum angle if I'm 100 metres up? And then trying to get down to this plane of field here. So I'm higher than where the object is falling to. Yeah? Because this is a question that might come up in one of the multiple choice ones, either for the weekly quiz. So I'm just going to reduce it so we can see it. So it does depend on the initial velocity. So I've got 45 degrees here, got no air resistance. Oh, still a bit slow. I did have all the velocities set before. All right, so we're only 10 metres up and I've got a low velocity. So I'm going to see if this is high enough to see the response. So now if we go up, let's have a look at the pathway. Yep, no, that's shorter. What about this way? What we should get is slightly further. So as you go below the horizontal of the projectile, that angle 45 degrees will not give you the longest range. And so you can try and draw the pathway below that. Obviously, the higher up you are, the more apparent that will come across. But yeah, so that 45 degree angle for optimum range will only play true for almost the same height. As you go higher, the angle will be different. We're not going to do that derivation, too complicated for this course. All right, so that's the range in reality. So we got this applications and research. I've come across this and I just thought it was a bit funny and weird. In fact, I saw it when I was in Adelaide Uni and then it came back. So there's actually been multiple research papers on this topic. And it's just projectile poo of penguin. I can't remember what the title is, but they must have used 5 different names for poo, such as feces, excrement. But anyway, you can use this same kinematic equations to solve that problem. Now, what that problem is, why they're solving it, I'm not really sure. But anyway, I can put those papers up. And it's peer-reviewed. Someone got a doctorate, yep. Yeah, and that's what I think it is really helpful if you draw that pathway or the expected pathway. But sometimes people draw the pathway they expect. So that simulation is really good at showing, that it's not actually the case. But yes, definitely not something we'll cover in this semester for sure. But yeah, it's definitely something that you can derive and calculate. So we've got one more example where I'll show you how we can solve a problem. So we have a shot putter. We've got a mass of the shot put. Probably don't need that today, but maybe next week we can incorporate it. So mass of 7.3 kilograms. We have an initial speed of 14.4 metres per second, and we have an angle of 34 degrees from the horizontal. So we're going to calculate the horizontal distance travelled by the shot put as it leaves the athlete's hand, and we've got a height of 2.1 metres above the ground. So we're going to do that now. Oops, not used to wearing this because it's always flat. All right, so we've got an example. So the first thing I'm going to do is I'm going to draw the schematic for it. So we've got the Y. It's very bad. All right. Got the X and the Y. And so the initial position here, Y is equal to 2.1 metres, if that's easy enough to see. And what we're trying to find is the final position, X. Yep, so we're going to calculate that horizontal distance. We've also been given V0, and that was given as 14.4 metres per second. So, and we've got the horizontal angle here, theta, 34 degrees. So you can see that this is already going to use what I've already said about finding the initial velocity. So I'm going to start by putting down what we know. So in the x direction, what we're trying to find is x. We can find V0x, and that's by separating out the components. So for that one, we've got, is that right? Yep, so we've got V0x, that's V0 cos theta, like we've shown in the lecture slides, where V0 is 14.4 and cos 34 degrees. So you can find a value or you can just substitute that in. We've got 11.9 for that one, metres per second. So we have now X, we have V0. Sorry, I didn't realise it was on autofocus. There we go. And we can find the initial position X0, that's 0, being here. And then we can do the similar things. Oh wait, we've got one more. AX is 0. So now we can do the same thing for Y. So Y starts off at 2.1 metres. V0Y is going to be equal to 14.4 sine 34. And that's going to give us 8.05 metres per second. All right, and then we've got, that's our Y0. And this Y, at final Y, is actually 0. And then we've got the G, which is our acceleration in the Y direction, and that's going to be minus 9.8 metres per second. Very roughly drawn. So we can now start using our kinematic equation. So the one I'm going to pick that will give us the position is our R vector, and that's equal to R0, or the initial position, plus V0t plus a half AT squared. So I'm going to separate that out into the X and Y directions. So I'm going to find the X first because I can already see, so if we write this out, I can already see that we're going to get some simplification there. So we can cancel this out because the X0 is equal to 0. And the position X0 is also 0. So X is now equal to 11.9 metres per second times T. So I'll put that in brackets because I've got the units there just because we're doing that this week as well. So I've already got a simplified version for the position that we're looking for, but the only thing we need to find is time. So what we can do is we can use the same equation in the Y direction, and something that I mentioned earlier about using this equation when we need to find time. So Y0 is equal to 0. the final position, y, is equal to 0. The initial position is 2.1 metres high. And then we have our 8.05 t plus a half, or maybe 4.9 minus 4.9 t squared. So now we can use a quadratic. You can use the equation, you can use Google, and there's quadratic equations that you can simply insert. Did anyone want to have a go at telling me what the time values you get for this? There should be 2, shouldn't there? Using the quadratic to solve it. Can't see any calculators or anything out. All right. Well, in that case, I'm just going to take longer then. So t is going to be equal to 8.05 plus or minus the square root of 8.05 squared. And then we've got plus, what's that? 4 minus 4.9 times 2.1. And that's going to be over 2 times minus 4.9. All right, we're going to go up. So when you solve for that, you're going to get 2 values minus 0.23 seconds and then 1.87 seconds. So which one is the one that we want? Yep, that's right. So why isn't it this one? Yep, and it's also, that's why it's negative, because we're trying to find this position of y, and this is minus 0. So if we went back in time of 0.23 seconds, we'd find the initial position of y there. But yeah, so usually we'll have 2 positions, one on the way up and one on the way down, if it was a different example. All right, so we're going to use 1.87 and we're going to plug that into our equation. So we've got our equation here. Yep, make sure you can see it. So x equals 11.9 metres per second times 1.87 seconds. The seconds cancel out, we're left with metres, and you should get 22.3 metres. Yes. Yeah, definitely, yeah. That's right. Yeah, so that's one example. There's the example next week in the tutorial. We will actually look at a higher ground, so it's going to land on a roof over a shed, and you'll have to do slightly different variation. But the more practice you get done, the more easily these will come intuitively to you. All right, but other than that, there's some multiple choice questions on Canvas, and I'm going to look at the end of this week, and if no one's been doing them, I'm going to do them in class. So, because otherwise there's no point in having them. But otherwise, come down and see me if you have any questions. I've still got 5 minutes of this lecture, so yeah, let me know. Otherwise, have a good weekend. I'll show you one of the questions that is up there.